kind of statement, because of course one also has a kind of this properties, but we just started from two. From some reasons, maybe historically, formally, we just start from two. Yeah? This is such a kind of statement as if we write that 0 factor is 1. This is also a kind of assumption. Yes? Because in general, if we write n factor, this is 1 times 2 times 3 and so on up to n. Yes? So if we put here 0 from this equation, it is not exactly obvious what does it mean. So this is a kind of assumption, and also that we start from 2. This is also just useful trick or something. 1 is not prime because what? It has also divisor 1 and n, but not 2 divisors. Maybe just this, yes. Okay. If we try to find an answer for the question if the number of prime numbers is infinitely great, we can make such a kind of thinking that if it is true, we can multiply all the prime numbers up to the greatest one. We assume that this is the finite one. Add 1 to this multiplication, and such a new number, if we divide it by every of these smaller prime numbers, we'll get rest 1, because this is plus 1 of the n. So it is not divisible but by all the previous prime numbers. So this is a new prime number. So this is a kind of statement to show. Of course, this is a contrary statement, a theorem, proof. We should assume that we have such a kind of statements proving, of course. So tertium non datur and so on. But this is quite popular method of showing that there is no the greatest prime number. Okay, let us write it like a theorem. There are infinitely many prime numbers. Okay, a proof. This is from Euclides. The proof goes from Euclides. Suppose the set of prime numbers is finite. Okay, composite of numbers P1, P2 up to Pk. Let us consider a number P1 times P2 and so on times Pk plus 1 up to this multiplication. This number does not is not divisible by any of numbers Pk, Pi, I1 up to k, because the rest is always 1. As we will divide by P1, this will be something plus 1, because this is 15. It is like we take 2 times 3 times 5 plus 1. Yeah, this is 15 and 31. If we divide by 2, this is 15 plus 1. Divide by 3, this is 10 plus 1. If we divide by 5, this is 6 plus 1. Yeah? As a rest. Because the rest is always 1. So it if it is not prime, it should have another divisor P different from each Pi, which contradicts the assumption, because we assume that the set of prime numbers is finite and composed of these numbers, but we just find another. Different from each Pi, which contradicts the assumption. Of course, this is just a skeleton of the proof. We can also say that this number is a new prime number. This is one conception of the proof. This number, we can call it pk plus 1. Also, we can show that if it is not a prime, so it should have a divisor, and this divisor is not in this set, but this set should be complete. We suppose that this is a set of all the prime numbers. So if it is divided by something which is not in this set, so it can be also divided by another, but from devising by any of this elementary primes, we can say, we can always obtain the rest 1. So in general, this is a kind of thinking in which we assume that something is not true and show that it contradicts the assumption that this is the whole set. Have you any question to this? By the way, this kind of thinking gives us a kind of algorithm for counting, for generating the prime numbers. And in fact, this is used in some cases to generate the prime numbers. As you maybe know, prime numbers are very efficiently used in cryptography for making a cyber security. For instance, there is such a algorithm RCA, which is used to make digital signature or just making a cyber security in general. And it is based in using prime numbers for generating so-called public and private keys. And having a greatest, even very big prime numbers gives a possibility to have a cyber security method, a cyber algorithm for making a maximal security. In some sense, if we have a maximal prime number, maximal up to best knowing of the military forces, in fact, because big prime numbers are using just as arm. So if we have such a number, so we can use it, and the enemy does not. This knowledge, so it is possible to make a complete, clear, complete, secure communication. So prime numbers, big prime numbers are very important in cybersecurity. This is such an example in which an application of mathematical theory appears after 2,500 years. So it was invited in ancient Greek, and up to 20th century, the application was just, this is a kind of play, mathematical play. But if computer security method appears, it was used up to after 2,500 years. So if we ask mathematicians what is this was working, and they said, this will be used after 2,500 years. So this is classical example, and any mathematician said such a statement that this knowledge of future of nowadays mathematics nowadays is for applications after very long time. Okay, so this proof seeming suggestion for the algorithm or generating successive prime numbers, because I did, the proof suggests an algorithm for generating prime numbers. Let us consider a sequence defined by recursion. Consider a sequence defined by recursion. E1 is 1, En is E1 times E2 times En minus 1 plus 1. The elements of the sequence are called Euclid numbers. The beginning seems good. Because on the beginning we have 1, this is E1, E2, this is 1 time plus 1, this is 2, and next we have 1 times 2 is 2 plus 1 is 3, 2 times 3 is 6 plus 1 is 7, 3 times 7 is 20, just a second. Yes. No. 2 times 3 times 7 is 6 times 7 is 32, is 43. But here appears a little bit different situation, because if we multiply 2 times 3 times 7 times 43, it is 1,807, and unfortunately this is not prime. Of course, the thinking here is that the number of natural numbers is finite, yes, but here we use on the part of them, so unfortunately this algorithm doesn't work. That means it gives a prime numbers, but up to 4. Next one is not prime. You can check. I don't know what is the divisor of 1807. We can check, but this is not prime, fortunately. So such a suggestion seems good, but unfortunately that does not work. The problem of finding of an algorithm on generating all prime numbers efficiently is still an open problem. Of course, we know some methods. We can give here an example of at least two of them. One is so-called Eratosthenes sieve, and this is for finite set a method of erasing not primes, obtaining on the end only prime numbers. The algorithm, as I remember, I have used before, was and it is usually done in such a way. It is done in such a way that we propose a candidate for being prime, and we divide by previous primes. And if nothing of them devises our new candidate, this is prime. So such a method, of course, works, but this is still very time-consuming. Of course, we can divide only by previous primes and divide only up to the square root of this number. It is enough. But still, this is not efficient method for real big numbers. Big numbers means that has, for instance, 100,000 digits. This is a big prime. And so if we try to divide by previous primes, it is very time consuming, and we need really powerful equipment to compute such a task. Of course, in military applications, this is done, but this is still very time consuming. Maybe let us write these two possibilities. So this doesn't work. Yeah, maybe I write it. It doesn't work, unfortunately. So another method, so-called Eratosthenes sieve, maybe approach one, example one, but example, negative example in this sense, it doesn't work. Example two, Eratosthenes sieve. Sieve. I don't know how to explain the sieve. Sieve means if we have such a kind of tool in which we have a small holes, as this used for many, for example, in road making. Yes, we use sieve of obtaining a small granularity of for instance, some rocks or something, stones, and so it works in such a sense. This is very effective, but for the finite set. Let us assume that we will look for all prime numbers not greater than 15. So let us write all the numbers from 2 to 15. If you have a possibility to turn on the cameras, it is very helpful for me to making the lecture, because in other case I just say to the plastic box. And this is not very I'm not very happy from making Okay, so let us say 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We should make a memory space, a table in the computer memory for all these numbers from 2 to the greatest one. And next, we choose 2 as the first prime number because it is divided only by 2 and 1. We choose 2 as the smallest prime. Prime and erased every multiply of 2 from the sequence, from our sequence. So we remove 4, 6, 8, 10, 12, 14, and so on. Next, among undeleted, okay. Next, from undeleted numbers, we choose the smallest one greater than 2, yeah? Greater than previous, then previous one, and continue the process. And so now we erased multiplications of, where's the black one? Somewhere. 3. So we remove 6. It is removed. 9. 12 is removed. 15. Okay. So next we choose the next one. 5. So we remove 10 and 15. It is removed. 7. We removed 14. It is removed. 8, 9, it is 11. That's all. We can, in fact, we can stop, I think, in a half. But let us continue up to the end. 11 on 21 is out of the table. 13, also 26 is out of the table. This is all. We continue the process. Maybe up to the last, the greatest, last one. Probably we can stop in the middle of the table. I think so, because if we are here, multiplications are out of the table, so it is enough, I hope. Is it clear? Of course, what we obtain is a set of prime numbers. 2, 3, 5, 7, 11, 13. So, by the limitations, the constraint of this method is that we have a finite set, yes, and we find for prime numbers in this finite set, and this is really hard. We can compute the computational complexity. However, the frequency of appearing of prime numbers is not also not very intuitional. We'll say something about it in a moment. But in fact, prime numbers are the distribution of prime numbers is also a hard mathematical statement, question. Maybe somehow still open. but as we can intuitionally see, the prime numbers appears in the bigger and bigger numbers. The question about distances between prime numbers is not obvious, but we can see, and this is also a kind of statement, that the twin numbers appears infinitely, and so we'll have still the numbers with distances too. Okay, any questions to this approach?
No, sir, thank you.
Oh, you are there. I'm happy because see, if I'm talking to the black table, I'm thinking, are you there? Another method, quite intentional, is iterational generating of primes. Example 2, 3. Constructive algorithm. Of prime numbers generation. If my letters are quite readable or not, what are you thinking? Maybe I'll make a kind of dictionary. You see, this is U, this is N, this is R, this is H, W is also similar, V. Almost all the letters are very similar to each other. Maybe it will be helpful.
Sure, they all look so similar, right?
This is U, remember, and this is V. Okay, so an algorithm. Let us try to write it in such a way. We'll generate candidates. Okay, so let us make a kind of loop. For I, let it be to n. Of course, we can make it as also as an infinite loop, but let us make it finite. If we use here while, it will be infinite loop. This will be a kind of candidate, and also we need a table of primes, int primes prime. This is a table of size, max size. Also, we need a kind of counter. So prime counter now will be 0 of the beginning. So we have no prime. Maybe let us write some of them. Okay, maybe not. And now, if we have a candidate, we can check if this candidate, checking if an candidate I is divisible by previous primes. So how to check? Let us make us a kind of bool variable is okay. True. Next, we should make a counting. So while maybe some a kind of maybe j let be 0. While j is smaller than prime counter, yeah, we try to divide. Yes, so we make a division in like that. If this I divided by where is this? Divided by prime, yeah, prime j. If this is 0, yeah, so it is without the rest. That means this prime divises I, and this is not prime. So in such a case, we write is okay, is not true. So it is false. False. In fact, we can in this moment we can just go. So we can write in such a way, yeah, that we just exit of this this loop, yeah. And next we check if is okay is true, yeah. So true. We can add this candidate to the next to our set. So we just write that prime. We should add something to this counter. So prime counter is this candidate I, and of course this prime counter at 1. Of course, we can do it here, but but doesn't matter. And that's all, I think. Of course, this will be this loop is here from here to here. This is something like C++, but in another notation. It doesn't matter. You know what's happened probably. And that's all. In fact, here it is enough to not dividing by all the by primes, but up to the. In fact, here it is enough, as I remember, to j smaller than the square root of this prime. Sorry, up to square root of I. But we have to take here a floor, a ceiling. So this is just a proposition. Of course, this algorithm can have some errors, but the idea is to try to divide by previous primes. Have you any questions, remarks to this approach?
No, thank you.
Thank you, sir.
It is almost 10, so let us make a 15 minutes break. So 15 minutes break, and after the next. Thank you. The break. I will be back.
Thank you.
Thanks. Hello again.
Hello. Hello, sir.
I'm back. We are still in prime numbers topic. Let us try to make some more properties of the primes, because they're really useful for many cases, especially for cryptography, but also just as properties for showing the dividers of the smallest common multiply of numbers. Let us write by such a notation a number of primes not greater than n. This is a little bit strange measurement, but let's try. If n is greater or equal to 1, let Pn means the number of primes, prime numbers not greater than n. P from n. Not greater than n. For instance, we can write such a kind of table. So we have maybe let's write the previous primes: 2, 3, 5, 7, 11, 13, 17, 19, 21, not 23, probably 5 not 27 not 29, 31, 33 not. No, let's do this. Okay, so we have here I, and this will be pi or n, n, pn. So 0 is 0. From 1, this is also 0. 2, this is 1. 3, 2. 4, 2. 5, 3. 6, also 3. Of course, for all the even numbers, this will be the same as the previous odd. For 7, this will be 4. 8, 9, 10 also. For 11, 5, and so on. Yeah. And it can be shown, although this is extremely hard from the theoretical point of view, it can be shown. The proof is difficult. That for a large n, we have the p from n behaves as n divided by natural logarithm of n. So this is a kind of distribution of the prime numbers inside natural number set that behaves like this. So the number of primes does not grow linearly, but a little bit slower. This dividing by logarithm, of course, means not. If we look how n by logarithm n looks like, maybe just a second, I will show it in some simple tool. Let's use Wolfram Alpha. Plot n by logarithm n. Yes. So of course this beginning doesn't matter but for greater one, it looks like linear, but in fact this is not. This is a little bit change the direction slowly, but almost linear. How to make the interval? I don't know really. Like this. I don't think so, but maybe not. I don't know how to make here a plot on larger intervals. You can check somehow. Yeah? But for us, this is important that it looks like linear function, but it slowly the curve slowly turns in this side. This is under the linear, but behaves very similar to linear function. Okay. It is in fact a quiet observation that every natural number greater than 1 must have at least one prime divisor. This means that any integer greater than 1 can be represented as a product of prime numbers, and the product is defined this so-called factors. We call these divisors factors. Let it be 15 is 2 times 3, 3 times 5, and this is factorization, factors. And this is factorization. Okay. And now we can write a kind of theorem, which in fact is a kind of base theorem of arithmetic, you can say. Theorem, even a fundamental theorem of arithmetic. That each natural number n greater than 1 can be represented unambiguously, which means in only one way. Of course, with accuracy to the order of factors, because this is 3 times 5 and 5 times 3. Yes? As a product of the powers of the prime numbers. The powers, because some numbers, as let it be for 27, it can be written as 3 times 9, 3 to the power of 3. Yeah. So this is a prime number, but 3 times. Yes. So we can factorize a number as a multiplication of the prime numbers, but sometimes some of them are in the power of. In general, in this factorization, we can have all the prime numbers, but some of them are to the power 0. Yeah, so this is one. Any questions to this moment? Okay. So by the formula, we can write it in such a way that a number n can be written as a product of pi to the power of ni, I to the power of ni, where ni are hardly strongly greater than 0 for every I greater than 1. Only one is a strange, a little bit strange, but one can be written as, let it be, just as 1 or as a 2 to the power of 0. But the rest of them, we just write as primes to the powers, where pi prime numbers. Okay, even we can write a kind of representation of n. Let us try to make something like this. Let us introduce a kind of representation, rep. So we can write in such a way that this is a sequence of these powers, yeah? And I greater than 1. That means that n can be written as this product. I greater than 1. What does it mean? For example, if we take 15, we can write that this is 2 to the power of 0, 3 to the power of 1, and 5 to the power of 1. Of course, this sequence is infinite, but here we have prime numbers. This is 2 to the power of 0, this is 3, this is 5, this is 7, this is 11, and so on. So, in fact, it is enough to write only the powers to represent any numbers, these powers of prime numbers. It can be useful because, of course, another question is how to obtain these factors. And in fact, this is a hard question. Up to now, there is no polynomially solvable, polynomially computed working algorithms. It works in polynomial time to make a factorization of a number. So if we have, let it be 20,701, so the question is what prime numbers are here. The only way we know is just to try to divide by 2, divide by 3, divide by 5, and so on, observing if we have right factors. I don't know any other algorithm. Of course, there is a polynomial time solving algorithm of this. This is so-called, it's not polynomial, polynomial solvable. Except quantum machine, quantum computer. In quantum computer, we have so-called Shon algorithm. And the Shon algorithm gives us an algorithm which works in time. I don't remember exactly. Square root of n. But this is polynomial, but we need, in fact, very powerful quantum computer to compute even smaller examples. So up to now, if we have machines which has up to 5,000 qubits, it is possible to make a factorization of really small numbers, maybe up to hundreds. So it doesn't matter in sense of the application in cryptography, where we have numbers in keys which has millions of digits inside. So it is not applicable in fact, but formally this is not so solvable in classical computer, but possible in quantum computer because of behavior of this machine, which is different. By the way, on the quantum computer, even we have a special class of computational complexity. As you know, we have P and NP, a computational complexity class, but there is also a special class designed for quantum applications, which is proven to not belong to P nor NP. So this it happens nowadays, but the quantum computers, as I observe, it is like early 50s of the previous century. So when we have had Dijkstra, algorithm, Bellman-Ford. This is such a time for quantum computers, beginning of informatics on these machines. So this is very beginning, and in fact, we have also only a few special algorithms for these machines. And really, machines are very small size and very expensive. Such a computer costs about $15 million and can solve really small examples, being called to almost zero Kelvin temperature. So this is really the hard for now. Okay, so in such a representation, we can show some examples. Let us take, for instance, 18. So 18, this is representation of 2 to the power of 1 times 3 to the power of 2. So we write it as 1, 2, and 0. This function has some useful properties. This function has some useful properties. So let us assume that we have two numbers, m and n, and the representation of n, let it be a sequence of ni, and the representation of m, let it be mi, for m1, m2, and so on. And also let us take representation of k. This will be k1, k2, and so on. Then, of course, we can write that n is a multiplication of this pi to ni, for a greater than 1. M is a multiplication of pi to the power of mi. And if we take n times n, so multiply these two numbers, n times m, will be pi to the power of ni plus mi. An example is, let us take here. If we have 3, representation of 3 is just 0, 1. Representation of 15 is 0, 1, 1, so because this is 3 and 5. So a representation of 45, this will be 0, 2, 1. Let us check. This is 2, this is 3, this is 5. So this will be a representation of 3 to square times 5 to the power of 1. And so this is 45. So it works. So we just add these positions here, yes, here, here, and so on. We add them. So this is quite useful. Because if we compute the greatest common divisor, we can use these properties easily, because this, which means that any k, which is n times n, can be written as in such a way that for all I greater than 1, key a in this representation of the multiplication is just ni plus mi here, yes, because k has the representation which is multiplication of pi to the power of ki. So this is our ki. Yeah? So if we consider n, if n, what is n divided by m, or just such a division, we can write that for all I greater than 1, ni should be smaller or equal to mi, and we conclude that k is the greatest common divisor, if this is true, which means that for all I, we can write this key A as minimum of ni and mi. This is quite useful. I will show it on an example, because we just have two numbers, let it be 45 and 15, and if we are looking for the greatest common divisor of two numbers, as here, we have 14 and 15, we are taking the minimal values of these positions. So here is 0, this is 1, this is 1. Yes, this is 0, and this is 1, and this is 1. So in fact, we will obtain 15, yes, as the greatest common divisor of this number. Let us take a little bit greater to show the working of this. An example. Which one? Next example. A representation of 16. This is 2 to the power of 4. So this will be 4, 0, 0, 0, and so on. Yeah? Let us take also representation of 24. 24 is 6 times 4. Yeah, 6 times 4. So this is 2 to the power of 2, and 6. This is 2 to the 3 to the power of 6. So we have 2 times 3. Yes. 24 is 4 times 6. So this is 2 times 2 times 2 times 3. Yeah. So 3 times 2 to the power of 3, as here, yeah? And 3 once. And now, to obtain the greatest common divisor of 16 and 24, we're just looking for these columns and taking the minimal one. Yeah. So the greatest common divisor, and this representation of the greatest common divisor, a representation of the greatest common divisor of 16 and 24 will be like this. 3, because this is smaller here, 0, 0, and so on. So we have, in fact, 2 to the, this is representation of the 2 to the power of 3, so this is 8. 8 is the greatest common divisor of 16 and 24. Of course, this is a kind of algorithmic approach to this problem. How to compute the greatest common divisor in computer. Factorize and next observe the minima of these factors. Is it clear how it works?
Yes.
Okay.
Yes, sir, it's okay.
In similar way, we can obtain the least common multiplication because we just take the maximal here. And this is also a kind of informatical computer science approach. Yes? Similarly, how it is written? Next, we have if k is least common multiply of n and m, it means that for all I, we could take key A as a maximum of ni and mi, and similar here, the representation of least common multiply of 16 and 24 will be 4, 1, in some sense. This is 4, 1, zeros. So in fact, we have 2 to the power of 4 times 3 to the power of 1. Yes, so this is 16 and this is 3. What is 16 times 3?
6 times 48, sir.
Sorry?
48. 48.
40.
8.
8. Okay, because this is 16 times 3, so this is 8 times 6. Okay, and this is great. The least common multiply of these two numbers. So intuitionally and algorithmically, we can compute it quite clearly. Of course, we know that the least common multiply from the by the way, least common multiply of n and m is the n divided by greatest common divisor. Yes, of n and m. So we can check, because the greatest common divisor of this we can. Right, the least common divisor of 16 and 24 is the multiplication 16 times 24 divided by 8. Yes. So let's try. So here we can use 2, so 48. Yeah. Because except 16, I can write 2 because here is 8 in the denominator. So it looks that it works. Mm-hmm. In fact, basing on this approach, we can also introduce a kind of property we call being relatively prime, because prime numbers is a kind of general property, but two numbers can be also relatively prime, which means they have no common divisors. So let us introduce such a thing. We call natural numbers n and m relatively prime, and which we denoted m such a sign n if and only if greatest common divisor of n and m is 1. So they have no common divisors except 1. Okay. So it is quite easy, because if we use this representation, we can observe that if they are relatively prime, we'll have no common divisors. Yes. So example, let it be 7 and 12. Yes. So if we write 7, the representation of 7 is just 0, 0, 0, 1. Yes, because this is for 2, this is for 3, this is for 5, and this is for 7. And the representation of 12 is 3 times 4. So this will be 4 is here to here, and 3 is just here. Yeah. So if we look for the common divisors, there are no common places. Yes, here the smallest one is 0, here is 0, here is 0, and so on. Yeah. So in fact, if we write it, if we write the representation of the greatest common divisor, sorry, where is this? Just a second. This is important one. Sorry, I'm back, as Terminator said. in some which Schwarzenegger's moves. Okay, so this is a kind of method for computing the easily greatest common divisor. However, we can see that this method is quite elegant, but not very useful practically, because as I said, for computing the representation in factorization, we can try to divide by all the prime numbers, checking if the rest is zero. So similarly as computing the prime numbers, generating the prime numbers. So this is useful, elegant, but not very helpful. And in fact, the method nowadays of factorization of numbers, of checking or dividing by the previous one, is based on brute force approaches. Especially that if we have the application in cryptography, the method in many approaches is to find P1 and P2 great, since big prime numbers, and compute P as Pi times P2. So if we have really great prime numbers, two of them, and make a multiplication of two of them, so such a result has only two divisors, this one and this one. So let us imagine that we have a very big number, which means million of digits, and we are trying to factorize it, but this number is a multiplication of two prime numbers. So we are trying and trying up to the moment we choose the smaller of this one. Let it be a number which has 60,000 of digits. Yes, and this is the first moment when we obtain the first factor. We divide by this factor, obtaining this one. And in fact, nowadays, this is the only method of hacking RCA method of cryptography, which means finding if we have a public key and a private key, we should try to make some kind of factorization of the product of something. And this is extremely hard in sense by brute force. It can take thousands of years, yes, by using our computer because of size of these numbers. Maybe, as you know, if we maybe even we can try if we take any address of the mBanking, let it be mbank.pl. Yes, this is here, and this sign means that this is SSL. And if we use, if we try to see this secure connection, this is SHA. Yeah, and here we have just a moment public key RSA. You see 2048 digits. This means binary digits, but this is the size of the key. So this is a number of digits, binary 0, 1 of the numbers. And this key, of course, this is written here hexadecimally, but this is a kind of size which should be broken. So we should find a multiplication of the numbers which has about thousands of digits. So in fact, this is a kind of the scale of the problem in such a case. Of course, by using quantum computers, theoretically, this is possible, but I think we are the last one to know it, because if the military forces, the army has such a computer, this is not public knowledge. So I suppose that this is possible nowadays, but quantum computers are quite not popular, and maybe this is an aim in some sense to not being popular. Okay, any questions, remarks to today's lecture?
No, sir. Thank you for this.
So thank you very much, and see you next week. Goodbye.
Thank you. Bye.
Thank you.
Thank you.
Thank you.